I'm Bruce Sinclair, and this is the Private Equity Digital Transformation Show, where we talk about the next big thing in value creation. This episode is brought to you by Digital Operating Partners, creating enterprise value by leveraging the smart megatrend to transform traditional companies into digital companies. For details, go to digitaloperatingpartners.com. With me today on the Digital Transformation Show is David Wentzloff. David co-founded Everactive in 2012 and is currently its co-CTO. He is also a professor of electrical engineering and computer science and the faculty director of the Center of Entrepreneurship at the University of Michigan. As with all my guests right now, Everactive is part of the Digital Operating Partners ecosystem. David, welcome to the show.
Thank you, Bruce. Glad to be here.
Seems like you got a pretty good gig going, but how do you balance the academic side with the commercial side?
A great question, actually. I think they really play off each other or benefit from each other. When we founded Everactive, we spun some technology out of the University of Michigan, as well as the University of Virginia, where my co-founder, Ben Calhoun, is also a professor. And so really the key differentiating technology inside Everactive was born out of those university research labs. And I can say just, based on my experience at the company, being able to talk directly to customers and get feedback on what their pain points are and where technology can really benefit them, I think that has really helped shape the research directions in both mine and my co-founder's university research group. So it really is a symbiotic relationship.
Now, how do you balance your time? I mean, are you tenured yet, or do you how do you break up your week then?
Yeah. So I am tenured and a full professor at U of M, and I'm on a reduced appointment at Michigan, which frees up some time for me to focus on the company too.
Nice. No, it seems like the best of both worlds because you have the security of being tenured, and then you can go nuts on your startup, and then I mean this one's working, but they don't all work, right? And so it's kind of nice. You got that stability. You got
Yeah,
the intellectual curiosity part. You can dig into all these different areas. You can see one that makes sense, and then spin it off into a startup. So it's kind of, yeah, like I said, you got a nice little gig going there.
yeah, it's great. I love it, and I really do enjoy working with students too, and teaching. It's something I've always enjoyed doing, and I'd say the one of the great things about being able to start a company and commercialize the technology is you get to see the technology that comes out of your research lab being transitioned into the real world. And go ask any PhD student who recently graduated or graduated 20 years ago, whatever happened with your dissertation or your thesis. And probably, 9 times out of 10 or maybe more, it'll be on a shelf, right?
Yeah,
So I
yeah.
think, that has certainly been a fun part of this journey.
Now, talk to us a little bit about the technology transfer for U of M, and maybe it was U of V as well. I don't
Yep.
know, but what's the business relationship look like? Maybe you can just give us some broad strokes on that.
Yeah, sure. So we do patent the inventions inside the universities. And
So
so
they own the patents
the
then.
universities will own the patent. Yeah. So University of Michigan, for example, owns some patents that have come out of my research group, where the students and myself are the co-inventors on those patents. And then Everactive has a licensing agreement with the university to exclusively license those patents with worldwide coverage and no restrictions on the use, and the ability
Okay.
to sub-license too.
So now is this a pay as you go licensing fee, or is it more upfront, or how does that work?
Yeah, it really
Based
does
on
vary.
sales or
Very,
time, or
yep. Yeah, kind of yes and yes. Time in the beginning and then sales more recently. But it really varies university to university. It varies based on the technology and the type of company, right, and how sales work. You might do something different in biomedical applications than, semiconductors, for example, and pharmaceuticals, right? Those might all look very different. So for us, we have a tiered milestone payment system set up where different milestones are triggered based on sales,
Nice.
or different like patent award milestones, like when patents are granted, for example.
Okay. Okay. And if we look at the P&L, uh, how do you account for that then? Is it, or and maybe that's not important, but more, I guess, where I'm wondering for people listening and where I'm going with this
Yeah.
is, what is the business dynamics of working with the university, and what would be the associated licensing fees? Are we talking, less than 5% of revenue? Are we talking less than 10, less than 2? Just roughly. I don't need to know exactly, but it'll just give our listeners a bit of an understanding of what this beast looks like.
Yes. Yeah. Again, I think that's going to vary for the nature of our business. We're licensing chip technology from the universities, but at Everactive, we design our own custom chips that are partly based on that technology and then partly based on designs we've done in house now. So it's some fraction of the chip that's based on that university IP, but then that chip goes into a sensor that we then build, and that sensor gets deployed, with a network, a series of gateways that we also stand up at our customer site. And then data starts streaming directly to the cloud. And then we have a cloud dashboard and,
Sure.
all of the insights that we deliver to our customers. And we sell all of that as a subscription in a subscription or service-based model. And so when you try and quantify, well, what fraction of that revenue stream is the patent from the University of Michigan or the University of Virginia or one of those patents, that's where, just to throw some numbers out, like single digit percentages, low, kind of ones or twos
Okay.
percentages. And, for fees, then, less than that from a revenue stream. But the thing I love about just the working with the universities is, again, I mentioned earlier, it's a symbiotic relationship, and it really does go both ways. And I think both universities have been very supportive of what we're doing at Everactive, and I think they're proud of the fact
Yeah,
of
of
our
course.
success to date. And obviously they get value from it through milestone payments, but also just sort of the notoriety of it
Yeah.
as well. And
Branding and yeah.
so yep, all of that. So it's been a great working relationship with those teams, and it just kind of in general, I'm really happy with how things have gone there.
Yeah, yeah. No, I think that makes a lot of sense, and a lot of universities, and maybe it's most universities, have an office, where you can interface with the office. You obviously are on the
Correct.
ground floor. You are doing the research and then
Yeah.
commercializing it, but it could be some of our listeners maybe want to work in a specific field, and they don't have the PhDs. But you know what? Grad students are awesome. You can point them in a whole bunch of directions because sometimes they're not really sure where to point them anyway.
Hmm.
And if you have a company that has a substantial and meaningful research project, and you have a grad student that's looking for a substantial and
Yep.
meaningful project, then it's a great way to get together. And then you're saying that the fees seem very reasonable too. So I think that's awesome.
Yeah, grad students are ambitious. You know, they're enthusiastic. They've got nothing but time on their hands. They're eager. They're not afraid to fail. I mean, you pull all these things together, and you can do a lot of very creative things in a university environment. So, yeah, for any of your listeners out there who are maybe considering sponsoring some research projects within universities, I'd say definitely give it a try. It's a great way to try out new technologies or to get kind of firsthand experience or firsthand input from the researchers directly.
Yeah. Well, why don't we pull back a little bit, and I want to dig into the intellectual property actually that you licensed, because it's not what I thought it was. But why don't we first start with what is it that? Well, first tell us about your background a little bit more. We've talked about it, and in particular your commercial background and maybe how you got involved, and then and then what the specialization of Everactive is.
Sure. Yeah. So my background, as you mentioned at the top of the podcast, that I'm an electrical engineer. I'm a professor of electrical engineering at U of M. So I am an engineer by training, and my specialty is in low power wireless communication. And in my research group, we focus that on self powered systems. And I have been collaborating with Ben Calhoun, my co-founder, for gosh, probably 14 years now or so, um, on on pulling together these complete systems on chip to implement self-powered devices, self-powered IoT devices. So, Ben's research group focuses on digital integrated circuits and systems. Mine focuses on wireless integrated circuits and some analog integrated circuits, and those two things dovetail to form these complete systems on chip, meaning a single chip that can do sensing, processing, has memory, has energy harvesting capabilities, and then has a radio in it for wireless communication, all
Right.
on a single chip. And we've been demonstrating some of the world's lowest power SoCs within our research groups, and that is the technology that we have transitioned out into Everactive. And that forms, that is the differentiating technology. That custom low power chip that we build is the differentiating technology that allows us to do so much more on so little amount of power.
Right. Right. Okay. So I understand the low powered networking part of it. We need it really low because we
Hmm.
don't have a lot of power.
Yeah.
I understand I guess your partner. Uh, it sounded like it was more the. Is that more the design of the actual chip itself? You said the digital. What was the terminology that you used that he's focused on?
System on chip is
Yeah,
kind of a semiconductor industry term to describe, an integrated circuit that has multiple
it's got
components
it
in it.
all.
Yeah. Okay. Yeah. So an SoC is the abbreviation of that. An SoC would include digital components like, for example, at Everactive, our SoC includes a 32-bit ARM processor in it.
Okay, okay.
So there'll be a
So the
digital circuit,
computing, the memory,
computing,
and then the
memory.
I/O,
Yeah.
is that kind of what it covers in?
Yep, correct.
All
All
right.
of all of the above. And I'll
Okay.
add in there, which is another thing that I think is something that we leverage significantly in our products at Everactive, is because we develop our own chips, our own very low power chips, and we can implement low power digital circuits in there.
Mhm.
Beyond having a general purpose ARM processor that can run, let's say, run any software you want, kind of within some boundaries, we add hardware accelerators, they're called, which are digital circuits that implement algorithm functions. And I'll spare you the details, I will stay out of the weeds, but you can use these hardware accelerators to offload very processor intensive compute from the main general purpose processor
Mhm.
to a very specialized specific accelerator. And the advantage of doing that is if you implement that accelerator at low voltage and very low power, then you dramatically reduce the overall energy consumption for that chip to compute a task, or I'm sorry, to do a task, where
Mhm.
that task might be analyze the vibration on this motor. Tell me the highest frequency components of the vibration coming off this motor. That would be an example of a task or an algorithm that you would run. And just to put some numbers on it, typically offloading onto a hardware accelerator like this can save around 100x in terms of power
Mhm.
consumption. So it can
Mhm.
reduce the power for that specific function by around 100 times. So
Okay.
so dramatic power savings, not just a few percent, but a couple orders of magnitude. And which is why I say that is what enables us to do so much on so little amount of power.
So you kind of surprised me again because I didn't expect, and I guess it's your definition of what analyze is, and I don't mind if we go a little bit into the weeds.
Be
Um,
careful. Be careful
okay,
what
well,
you wish for. Yeah.
let's see where we go with this. But analyze vibration, I would expect if this is a sensor, and generally, what is a sensor? Now, you've mentioned digital a few times. Generally, a sensor is gonna transform one energy form into a DC current, and then that DC current is going to be inputted into maybe a system on a chip, and then it's going to package it up and then send it away, and to be
Mhm.
analyzed. Now, what you're implying here is you're doing some onboard analysis
Yes.
on the chip itself. I would have
Right.
expected your hardware acceleration to be for certain types of potentially matrix calculations or certain
Mhm.
types of, I don't know, solvers that
Mhm.
that you need
Mhm.
for energy efficiency. But maybe just shine a little bit more light on that for us.
Yeah, happy to. So I'll do that with some examples. So you mentioned a sensor and its function. So for example, when we are monitoring the health of a machine, when we're on a rotating piece of rotating equipment, like a motor, for example,
Hmm.
we have an accelerometer, a three-axis accelerometer, which will produce X, Y, and Z vibration data streams. It'll tell you the acceleration on the X, Y, and Z axes. And then we also have a magnetometer in there that is measuring the magnetic field around the motor. So motors
Right.
operate via electromagnetism. And so there's large magnetic fields that exist around a motor, and we can sniff those fields as well. So those are two of the, kind of very close to the motor sensors that we have in our self-powered device. So, which by the way, it gets its energy from the heat of the motor or the ambient light in the room, or both.
Okay, so it's not the vibration. I thought it was going to be the vibration. Okay, so it's the
No,
heat.
no, it turns out a healthy motor doesn't vibrate too much.
I guess that's
So,
true.
yeah. And if we're doing our job right, all
Yeah.
the motors are healthy. Yeah.
Right.
But there's enough heat. We only need a few degrees C of temperature difference to harvest. So, which you'll typically
And
get from a
differences
motor.
between the what you're measuring and the ambient
Yep.
environment is okay.
Yeah, that's right. Yeah, like the surface temperature of the motor, the heat sink fins on the motor, for example, and the ambient, just a few degrees C is enough to power our sensor.
Okay.
And so then getting back to the compute, so you've got these three accelerometer data streams coming in. You have this magnetometer data stream coming in. So from the three-axis accelerometer data, we do things like compute the total RMS vibration of the motor across all axes. We do that on the node.
RMS? What's RMS?
RMS is root mean square.
Okay.
It's
Okay.
a
So you're
form
just
of
a way to bring it together.
it's a form of averaging.
Yeah.
Yep. So it kind of gives you an overall sense of how much is this thing vibrating, and has that changed recently? Has there been a significant change in the overall vibration? So
Right.
that's one
So you're
example.
taking the positional information, and then you're taking the first and second derivative of that positional information to get the change in the vibration. Is that what
Actually,
something?
actually, getting a little more in the weeds, we measure acceleration, but typical machine health predictive maintenance technicians, they want to see velocity. They prefer to look at velocity. So we first convert acceleration to
Okay.
velocity.
Okay.
So that's our first
Yeah.
conversion on the
All
node.
right.
We do
So
that
you're
on the node.
integrating it. All right. Yeah.
Yeah, and then we do this further processing on it. RMS
Okay.
is, like I said,
Interesting.
it's simply like an averaging.
Sure.
It's there's a squaring function in there, but it's
Yeah.
more or less an averaging. You look at the data over time, you combine the three
And then
axes,
you choose a window, and then whatever that
use a
window is going to
window.
be for
Yep,
that
that's right. And
RMS.
you
Yeah.
you give an overall vibration
Okay.
number based on that. And then
A
and
vibration number in each of the three axes. Is that correct?
well, we combine them because what we've heard from our customers is it's enough to just have
Okay.
this
Overall.
aggregate vibration number. Yep.
Mm-hmm.
Um, for that particular need. So, but that's just the tip of the iceberg. Then you typically want to dig into well, what is the frequency signature of this motor? What are some of the high pitch, maybe not even audible, but what are some of the high pitch vibration frequencies that exist, or and how are those trending over time? And so we will we'll then convert that velocity data to the frequency domain. We do that on the node.
Mm-hmm.
And then we look
Okay.
at all those frequency magnitude pairs, and we pick a set of maximum frequency magnitude pairs. We bundle all that up in a wireless packet, and we ship it all to the cloud, along with some temperature and humidity measurements just around the sensor. We measure the skin temperature of the motor too, so we combine a bunch of other sensor data I haven't talked about. We put that in there, and we ship that all to the cloud along with some sensor health information. You know,
Okay.
um, so, and then once you're in the cloud, now you can apply the next level of algorithms, or you can look at trends. You can think about now AI or training models, machine learning models to analyze these signatures, look at the
Mm-hmm.
trends, identify
Mm-hmm.
anomalies, and then just to talk a brief moment about where we're heading with Everactive for our Gen 3 technology, which is we're currently designing the chip for that now. We have our first prototype chip back already. We're planning to push some of that edge or some of that machine learning computation down to the edge, down to the node itself.
Why not?
So for those who are familiar, we're planning to do some form of inference on the node. So it's kind of
Of
the
course.
first step of extracting some information out of the sensed data before putting it into a neural net, a fully connected neural net.
Well, yeah, for everyone listening, then inference is really just the execution of a model, that's been created. And then when you're talking about frequency signatures, for example, that could be a model, and then
Hmm.
potentially, I don't know, whatever application you're doing here, but then you could say, oh, this is my model, this is what's coming in, and then you could inference through the model and then do some calculations on, hey, everything's good here. No worries here.
Hmm.
Or is that kind? And
Yep,
then, oh no, we got
exactly.
some issues here. So let's actually give you some more data,
Yep. And then
roughly.
because we maintain that cloud connectivity, as those models get improved over
Yep.
time, as we monitor more and more machines, more and more assets, we can improve those models, and we can push those updates down to the sense
Hmm.
node to make so they get smarter over time.
Okay. So then, yeah, just to then go back to my original or my second confusion was on the analysis that you were talking about. Okay, what you did is got really under the hood of how a sensor works, and
Hmm.
it is taking the raw data and then even doing a pre-packaging of that raw data before
Hmm.
it's actually manipulated and the rest of it, and putting it into a form that's useful for analysis. And then your hardware acceleration, it sounds like, are for a number of these different mathematical
Correct.
operations that could be done on the GPU, but instead you're actually putting them in the hardware.
Yep. To
And
save
now,
cost.
and then what you're saying then going further is, since, hey, we're chip designers and we know there's going to be, there is a trend and it makes a lot of sense to do on, edge computing, then if there's very typical models, and then, or maybe you're just doing a general inference calculation of or execution of a model, we may as well put that in there too. And then if some customers want to use it, we can then feed that data stream that we originally kind of massaged through this inference model, and even send information, not just data, but actually send information back through the network. And we'll talk about that in a moment, to
Yep.
the cloud.
Yep.
Yeah.
Exactly. Yeah,
Okay.
and Bruce, I think where things start to get really interesting is we've been talking to some of our partners, as well as sort of putting feelers out in our network to put some structure behind and develop an ecosystem that will allow third parties to plug in to our full stack sense solution at different layers of the technology. And that might be an API in the cloud, for example, where our cloud talks to your cloud.
Right.
But in the future, well, we have that today. We have a public API today. But in the future, that could be at the gateway level, for example,
Sure.
or even at the self-powered node
Well,
level,
that's interesting.
where,
So how would you do it at the self-powered node? I mean, the gateway in the
well,
cloud, that's all, yeah, sure. But what
yeah,
about
yeah.
on this? Yeah, what about down there on the edge?
Yeah, exactly. So, our current thinking there is we would like to essentially open up a container
Mm-hmm.
where somebody can implement their own custom code on our node. So
Okay.
the hardware in this case would be fixed, where you
Right.
have accelerometers and temperature sensors and magnetometer, for example, a microphone, a camera in the future. Those are coming.
Sure. Yeah.
So you'll have access to these sensors, and you might want to run your own inference engine on the node, or your own proprietary algorithm to analyze that data for your application, whatever it is. And
Hmm.
now it no longer matters to us that it's a motor or a steam trap that we're monitoring. We're enabling others to take this technology and apply it to their applications. So that is that is something that we are working hard to enable in the future. We are a startup company, we're a small group, and we're pretty focused now on our product roadmap. But we've been thinking about the ecosystem and how we will open this up eventually, assuming we're going to get there. Assuming there's going to be a lot of demand for self-powered, sensing solutions out there, and people who want to plug in, like I said, at different layers of that technology stack.
Yeah. Well, it sounds like, yeah, we got a bunch of work for some PhD students, because if you do want to do it at the edge, then you're going to have to actually develop your own programming environment. I mean, so that people can actually program your chip, right? I
Yeah,
mean,
or
or
operating system. Yep.
right,
Or,
or okay.
yeah,
So
or
would it
agnostic.
be okay? Where is it going to be at? I mean, is it at the OS? I don't. Why would it be at the OS as opposed to at the algorithm at the application layer within the chip?
Well, let maybe think of it like so. If we have a like tiny OS, for example, or a very
Hmm.
lightweight
Yep.
OS running on the Sense node, then you can think of this more or less as an app that's running in that OS.
Okay.
So we
Okay.
open it up so that our customers, or a user of the device, could essentially install their own app and could plug in with all the appropriate drivers, can plug into the radio, plug into the various sensors, for
Right,
example.
right. And then we'll get out of the weeds in a moment. But the last question, I guess, maybe the last one is: you
Mhm.
mentioned container. Did you mean that in a literal sense, like a Docker kind of
Yeah,
architecture, or did you mean
that
it more generalized?
yeah, because we need to protect what we think about most is power. That's where our
Yeah,
mind goes all the
yeah,
time.
right.
And when you're running on a very limited power budget, you have to be very careful about what you do on the node. You can't turn everything on continuously and run everything at full blast if you're in a constrained energy environment at the moment. And so what we would essentially do within our operating system that's running on the node would be to manage those energy resources and manage what the apps are doing, and have a way for there probably to be some two-way communication here. Like,
Mm-hmm.
if we know on the node that we're rapidly depleting energy resources, and there, for example, the lights just turned off, so there's no new power coming, no new energy coming in, but we have some local energy storage still on the node. That information could get passed back even to the app or the app developer,
Mm-hmm.
who can then have, essentially modify what they're doing, or how, prioritizing what they do based on those energy resources. And in the extreme case, we can just shut it down,
Okay, so
and
so
pause.
that's why you containerize it. Is
Yes.
number one, it could also blow up, and then you don't want it
Yeah.
affecting other parts. And
Yeah.
but you can actually you put a limiter on the energy that container, or you give a budget, or they can give a budget to that container so that it doesn't overload, or it doesn't, I
Yeah.
guess, affect the operation of the sensor.
Yep. And I think if we've done it right, then the app developer or the software developer doesn't really need to know that information.
Okay.
We've
Okay.
abstracted that, much
Hmm.
much like your computer's operating system or your phone's operating system protects the phone. Uh,
So it
if
just wouldn't be
things
able to do something super energy cons, cons, con, consuming. Is that what
consuming.
you're saying? I mean, it just wouldn't be able to do that, because they could say, "Oh, we want to turn all the sensors on all the time and collect
Yeah.
all this data,"
Right.
but you're saying you don't have to worry about that because we're just not going to let you do that. Is that what you mean?
Yep. That's right.
Okay. Okay.
Yep.
So it'll be those type of constraints.
Yeah.
Okay, so interesting. I want to talk about where the uniqueness of your solution is. So number one, I think it's awesome, and we're going to get into the awesomeness of it, of why an energy harvesting sensor is awesome. But it's interesting. I would have thought that a lot of the science and the tech would have been in the energy harvesting part itself, but it doesn't sound like that. It sounds like it's more the energy management. Is that right? Is so? That's not really what's unique about your solution. Is not so much that you can gather using that differential of 3C. I think you said
Hmm.
uh, it's not so much that. It's more the, let's call it the OS, or let's call it the environment, but how you do it in a low energy form. Am
Yeah.
I interpreting that correctly?
You're interpreting that correctly. Yes. So, for example, we today our sensors can harvest from light or heat. So for light, we use off-the-shelf photovoltaic cells. We have two different flavors. We use one for outdoor, we use one for indoor. That's
Mm-hmm.
optimized for the two different light sources. But they are off-the-shelf PV cells. For our when we're harvesting from heat, we use an off-the-shelf Peltier device. They're called thermoelectric generators. They've been around for decades.
Right.
So
Okay.
these are not
Okay.
new technology. Neither of these are new technologies.
Right.
Now,
Right.
what is new though is if you only apply, a few degrees of temperature gradient across a tag, you only get about 40, 50 millivolts of voltage out of the tag.
Mm.
And that is exceptionally hard to extract any power from because it's such a
Uh,
small voltage.
right. Okay.
Usually, circuits that you'll buy off the shelf, they operate at 1 volt. We're talking about 100 times less volts. So 100 times smaller voltage.
Mm-hmm.
Okay, so it gets very hard to extract power from that. We have our SOC has a power management unit on it that can harvest directly from a tag. It connects directly to
Teg?
the
What's
tag.
teg? What's teg?
TEG, thermoelectric generator.
Got it. Okay.
Yep.
Mm-hmm.
So connects directly to the tag and harvests directly from that, 30, 40 millivolt signal that's coming out of the tag and can extract real power that we can then store locally in a capacitor and then use to power our entire sensor. Same's true for a photovoltaic cell, although it's kind of the dual of the tag. The photovoltaic cell, if you just put it in dim indoor light, it will produce a significant voltage, like in the hundreds of millivolts of range, but the
Okay.
current will be very small.
Right. Right.
So again, it's the dual of
Yep.
the tag, very low current, and our power management unit can harvest efficiently from that too.
Right. Got it.
So we've developed a circuit in our SOC that can harvest efficiently from these energy sources at low power levels and extract with high efficiency in the 90% efficiency, extract power from those harvesters. So
Got it.
and that is the first step, right? If you get that wrong,
Well,
everything
that's
else
the
just
secret
gets
sauce
way
too, right?
harder. Yeah.
Yeah. Yeah.
Yeah. So that's what we do on the power management side. And then I mentioned we have multiple other components on our SoC, processing. There's a 32-bit ARM core on there. There's memory. There's sensor interfaces. There's hardware accelerators. We talked about those. There's a
Mm-hmm.
radio on there as well.
Sure.
So we integrate all these blocks, and all of these are designed by us from the ground up with low power in mind and with a self-powered system in mind,
Mm-hmm.
meaning, at any moment, your source of power could go away. That doesn't mean you die instantaneously because you can store energy locally.
Oh, so you have like a
But
some
on a
sort of
capacitor, yep, not on a battery. We do not use any batteries in our sensor products. So because batteries wear out over time, and they eventually need to get replaced.
Yep.
So capacitors have a much longer lifetime. So we use capacitors for local energy storage, and so our the blocks, the individual blocks of the SoC have been designed from the ground up not just for low power, but assuming self-powered systems where you have this intermittent power source.
So that means if there's no heat or if there's no light. I mean, because that's your two sources
Yep, heat
of
goes
power.
away, light goes away. We still power
For a
for
little while, and
hours to a day for our current product.
that
It's
is
super
actually a big
low power,
surprise.
Bruce. It's super low power. So
Wow.
yeah, but that is something that we can engineer. We can tune that. It's just when the steam shuts off on a on a steam system, when the steam shuts off and the heat goes away, we watch the pipe cool down, and but then the steam's off, and at that
Hmm.
point, it's not super important to be continuously monitoring your steam trap.
Exactly. Yeah.
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 So
Yeah.
we can dial this lifetime after the energy goes away based on application, and that's what we've done for our first two products. Same's true for the motor. Once the motor spins down, it's just sitting there not moving. Eventually, after I, that one's closer to a day, 24 hours, we will stop reporting on that motor. But as soon as that motor turns back on and warms back up, we
You got
we
energy.
power up instantly.
Right. Okay. Um, so this is going to get us, kind of pull us out a little bit, but you talked a lot about the energy or the energy and the data that you are extracting from motors. So we talked a lot about the vibration.
Mm-hmm.
The steam traps is the other area, and I'm gonna ask you about maybe just describe steam traps and then describe what are you measuring on those steam traps.
Yeah, sure. So first, to describe a steam trap, so I will admit that maybe about 3 years ago, I had no idea what a steam trap was. So we were actually introduced to steam traps in this application by one of our potential customers. And so what a steam trap is really what it does is it traps condensate in a steam distribution line. So for a facility where steam is used, you will have steam distribution lines, pipes going everywhere, taking steam to the various
Mm-hmm.
loads. Condensate will form in those high pressure steam supply lines. That's bad. You don't want condensate in your steam supply lines. So what they do is at low spots at the steam supply lines, they will put these steam traps. They collect the condensate. When enough condensate builds up inside the trap opens. The pressure of the steam pushes the condensate out into a drain line,
Right.
and then the trap closes, and that process repeats about once a minute, once every 2 minutes. The trap will open and expel condensate.
Oh, okay. More frequently than I thought. All right.
Pretty frequently. So, all right, so these things are all over where you have steam distributed. In addition, when you have a load on your steam system, that load is going to be using the steam to do something, heat up a material, for example. And when that happens, the energy from the steam gets converted to heat up the material, therefore the steam condenses. And on the other side of that equipment, there will be another steam trap to collect that condensate and return that or put that in a drain line. But it's a pressured system. The
Yeah.
whole thing is high pressure, even through the equipment to
Yeah.
that
There's pipes
final
everywhere. Yeah.
pipes everywhere, and everything's pressurized. And when you add up all these traps, for a small facility, you might have 100 traps. For a large facility, we've seen 10,000 traps.
Wow. Okay.
So average, let's say average is 500 to 1,000, for maybe a food and beverage facility, or, like oil refineries, paper and pulp, those tend to have many more traps. Our smaller deployments tend to be like in HVAC systems where steam is used for heating and cooling. That's very
Mm-hmm.
common here in Ann Arbor at University of
Yep.
Michigan. We use
Yep.
steam to heat all our buildings.
Yeah, yeah. I used to have
You,
steam, yeah, in my apartment in Montreal, and it was actually really awesome. It's
yeah,
a really good way
yeah,
to
that's right.
heat up your place.
So,
But what is it measuring though? So getting back to the sensor, is it
sure.
simply you're just measuring change in temperature, or is there something
Well,
more?
right. I'd say the primary difference here is we continuously measure the temperature on the
Mhm.
supply and the condensate, the steam side and the condensate side of the trap. So we have
Okay.
two temperature measurements across the trap. We also measure ambient temperature and humidity in the
Okay.
air, but it's non-invasive. We clip onto the outside of the pipe and we continuously measure temperature. And the reason we can continuously measure temperature is because we are continuously powered by the heat of the steam. If you had a battery there, you would be trying to play the game of what's my lifetime and how many
Sample rate and blah blah
sample rate. Yeah,
blah. Yep.
yep. We don't play that game. We don't have to. We've got to
What are you sampling
continue.
at? Just out of curiosity.
We can program it down to every 10 seconds. We set it to about a
Okay.
minute.
Okay. Okay.
And for the signal processing people out there listening, a minute is well over Nyquist sampling for any kind of temperature events or temperature
Okay.
gradient.
That's what I'm wondering. All right.
Yeah,
All
so
right.
it's way oversampled at a minute, and which when you compare that to what's been done, to monitor steam traps before, it would usually be one inspection per year, or maybe one inspection every
Right.
3 years. Yeah, so sampling once a minute
So
is
it's
a
like,
bit of an improvement. Yeah. So so what we do is we ship that data to the cloud, and then we look for trends, anomalies, just
yeah.
deviations in that temperature. So we can detect things like intermittent blow-throughs. A blow-through is when the steam trap fails open and steam just goes straight through the trap
Yeah.
into the drain line, just
Right.
wasting steam constantly.
Yeah. Yeah.
So because the boiler just overproduces steam to maintain a certain pressure in the steam line, which means you've got a hole in the steam distribution line and steam's just leaking out into the drain. Very
Okay.
expensive. You lose about 100, $200 a week when that happens, based on
So
different factors.
so then what the reason you have two, it's going to be this differential is going to be the key, I'm guessing,
Well,
right? I mean,
that's we started with that. It's
huh.
no one had really looked at this before. We scoured, scoured anything public we could find on continuous temperature data on steam traps, and we came
Right.
up with nothing. Nobody
Huh.
has really
Huh.
deployed this that we are aware of. And so, we were the first to go look at it, and so we set out a bunch of sensors. Actually, University of Michigan was gracious enough to let us go deploy some sensors or very early on and just observe what we see in the temperature data while we would periodically go around and inspect those traps
Mm-hmm.
with an ultrasonic piece of equipment for trap inspection, a manual piece of
Hmm.
equipment. Walk up to the trap, touch the trap,
Right.
listen to it with headphones, and then assess the state of the trap. So we would walk around and monitor traps with this equipment while continuously monitoring the data. And some of our early assumptions, like that you'd expect the condensate to heat up when steam is blowing through, some of those assumptions were confirmed, but just straight up temperature differential across the trap, we learned, was not sufficient.
Hmm.
And so we train models to look for certain, various triggers. There's about a handful of different triggers that go into determining whether or not we think a trap has failed.
Okay, and those models then are not gonna look within this trap. It's gonna be intertrap, I guess. Is that right? So looking at the differences between different traps?
Nope, it'll be on a single trap, but it'll be
Okay.
on the temperature data over time.
Okay.
And that's
Okay.
that's the key difference here, is because we have continuous temperature data over time, we can look for various different types of signatures. Like, for example, the um, the variation of the temperature might change. Like when things are
Sure.
operating regularly, you might expect, like a noisy signal, right?
Mhm.
Some
Mhm.
wiggling on the temperature.
There should be a pattern. Yeah.
Should be a pattern, right? Yep, some spread of temperature. Well, when a trap fails, that spread changes. So there are
Sure.
things like that you can key in on in order to assess the state of the trap. So we had to go get smart on this and go train ourselves and train some models on what to key in on. But now we've got things pretty dialed in, and we're able to detect blow-throughs. We can do things like detect intermittent blow-throughs. That's where a trap blows through for about a couple hours and then goes
Mhm.
back to normal, and might do that for its entire life, once a day, twice a day. And so things like that you wouldn't normally catch if you're just walking up to measure the trap with an ultrasonic piece of equipment once a year. Your chance of getting it while it's blowing through are
Of
probably pretty
course.
low. And so, yeah, so we're able to observe things like that, so we can give much more fine-grained feedback and insights to our customers about whether or not we think it's time to change this trap, you know. So, and those are some of the insights I was talking about. Part of the service we deliver is just directly giving those insights to our customers. So through
Yeah,
alert,
no, absolutely. I mean,
follow up.
what's intriguing to me, is at the sensor level. But of course, at the sensor level, the value proposition in a big way is going to be continuous sampling
Mm-hmm.
because you've got the energy source and then also the maintenance side of not having to worry about the batteries and
Mm-hmm.
change the batteries.
Mm-hmm.
Um, but this is within a larger system, of course, like other systems. But if I look at what's very unique here, is going to be the energy harvesting and the ability to have a higher sample rate and not have to replace the batteries.
Yeah.
But of course, you're saying you've got gateways. So now, if we just zoom out a little bit for the audience, we've got these sensors. Dimensions. What are the dimensions of these sensors?
It's about the size of a tangerine, couple
Okay.
inches on a side.
So you need a little bit of room, so about the size of a tangerine. Then you've got some gateways,
Yeah.
and and whatever your network topology is for those gateways, and then it's going to go up to the cloud, like you said, and then your service. So you have a full service. Now we
Mm-hmm.
talked about two different use cases. One was rotating machinery. That's pretty
Mm-hmm.
self-explanatory. The second one was steam traps. And in
Mm-hmm.
steam traps, if we talk about use cases now, this is you mentioned food industry, you mentioned oil,
Mm-hmm.
pulp and paper. What are some other where are the situations where you would use where steam traps are used? Just for everyone listening.
Yeah, sure. Actually, I was surprised to learn that steam is very prevalently used in a wide range of applications. It's still a very efficient way to transfer energy over long distances. Transfer a lot of energy over
Yeah.
long distances. Steam,
Isn't that counterintuitive? It just seems so
yes,
prehistoric.
to me it was.
Steam. I
Yes,
mean, really?
yeah,
I mean,
yeah,
a steam engine. Think about that. Yeah, we're
yeah,
literally hundreds year old technology,
yeah.
but okay,
But it's
it's super
tried and
efficient.
true. Yeah, it's a very efficient way to transfer lots of energy. So it is used all over the place. So in cities like New York, Chicago, Detroit, steam runs through the ground in steam tunnels. It's distributed to buildings just like electricity and water and sewer. It's a utility. You can plug into the street steam. You can heat your building from steam that a utility in New York, for example, Con Ed,
And they got some big
produces
broilers that are somewhere, and
somewhere. And
they're heating up, I guess, water, and then they're
yep,
pushing through
shipping
the steam.
steam. Yep, because
Wow.
steam is
Okay.
an efficient way to transfer energy.
Yeah.
So they're shipping the steam, and then that's used for HVAC systems in buildings. We have a deployment in the Morgan Stanley building on Times Square. That
Hmm.
iconic building with the curved
Sure.
LED wall on the outside, for example. So HVAC systems where steam is used for heating and cooling.
Okay.
That would be one. I
Cooling.
mentioned
Cooling too.
cooling. Yes, cooling. So, I think this was born out of if you're in a facility where steam is a waste product, for example, a power plant will typically generate a lot of steam while making electricity. And so steam in that case is the waste product. Usually power plants have these tall stacks and steam comes out the top, right? Well, if you could take some of that steam and reuse it for something else, then you're saving there, right? Because you're making the steam anyway.
Hmm.
So refineries are kind of similar, where there's chemical reactions, and those chemical reactions are exothermal. They generate a lot of heat. They use
Okay.
water to cool the reactor, and when it touches the reactor, it produces steam. So now you have again waste steam. So you could obviously use that for heat, but you can use that in a heat exchanger to
like a heat
create
pump.
cold air. Yep. So so that's
Interesting.
HVAC systems. I mentioned paper and pulp. So really, with any wood products, there's a lot of drying that drying of the wood products, for example, or maintaining temperature through the process of manufacturing paper. So that's a big part of that industry. Chemical refineries, oil and gas, those
Hmm.
tend to have, those are the bigger deployments in our experience. But really, food and beverage has been another. Um, but really anywhere, you kind of think about where you might want to use steam for regulating temperature. Like we've even seen applications where steam is used to like heat up adhesive to seal closed bags. Plastic bags. Those plastic bags you rip open, right? They're closed with an adhesive, and that adhesive gets heated up, and it has to be at a very controlled temperature, and usually steam is used for that.
Yeah.
So so I was shocked to find that
Hmm.
steam is just prevalent in just about, if you're driving by a manufacturing facility, and it's like at least the size of a basketball arena, or something like that, it's almost certainly got a boiler in there and is using steam for something. It's probably got a few hundred steam traps in there.
Yeah, yeah, and I think maybe that's a good differentiator. Discrete manufacturing versus process manufacturing. On the discrete side, well, you got your rotating machinery, so that's kind of nice. You're covering the discrete side, and then I'm probably on the process engineering, and then that's all the above that you were
Yeah.
talking about. Then you're going to be using steam. They're going to be using steam, and ideally, I mean, specifically because it's an efficient way of transferring energy, which is
Hmm.
interesting. I mean, it's basic, but really interesting. Well, why don't we get into a case study? So, in terms
Sure.
of the steam energy
Hmm.
transfer and so forth, can you maybe take us? Because I'm going to start grilling you a little bit on the numbers.
Sure. Yes. So, well, maybe just to talk about the product for a bit. So I mentioned, I think a couple times now, we are taking this to market as a service. So it's a subscription. It's an annual
Okay.
subscription.
Yep.
And today, our price for one endpoint, we call it, or basically one to monitor one steam trap, or to put one machine health monitor,
One sensor.
one sensor. Yep. Where a motor might have one sensor, 1 to 3 or 1 to 4 sensors on a motor, depending on the size of the motor. But per endpoint,
Is that an endpoint? Is that one endpoint, or is that three or four
that would be
endpoints?
3 or 4 endpoints
Okay.
for a motor like that. So per sensor, we typically charge on the order of $300 per year per sensor. That price, goes down with higher volumes. It also goes down with longer term subscriptions. Signing up for 2, 3, 4 years. A lot of our more recent customers are doing longer term subscriptions. So that I think they're buying in. They're going all in.
Yeah.
They know they need some solution, and have been very happy with our products. So so that's sort of the base cost of the sensor.
Hmm.
And I mentioned that is an annual subscription. So we cover all the hardware. We manage the installation as well. We maintain those sensors so they are cloud connected. So we are able to remotely monitor them and maintain them because they're self powered and there is no battery inside. That maintenance is very low to none, and that helps keep our costs down, which
So you
keeps the
cover
cost.
that. That makes a lot of sense.
Yep,
So you
keeps the
cover if
cost of
there
the
is
sensors down.
maintenance is required, you're going to handle it. But yeah,
Yep. Yep, but it's small, and that basically that cost is essentially passed on to the customer
sure.
in that subscription fee. But if at any time we aren't doing our job, if we aren't providing value, then the customer doesn't need to re-up their subscription. And
And
luckily
you're
we
saying generally you're doing a year. You're trying to get a 1 year subscription. Nothing shorter than that, and then
nothing
sometimes it'll be
shorter,
multiple
yeah,
years.
nothing shorter than a year.
Yeah.
But typically, our more typical installations or sales more recently have been in the longer 3 to 4. year time frame.
Okay.
So
Okay.
yeah, so that is our business model and rough
I
pricing.
like it. I like it. I like it. Okay, so they got the pricing, and then
Yes.
just to put this now in concrete, you're mentioning a typical installation that's using steam might have 500 to 1,000 traps.
Yeah.
So we're talking about anywhere between 150 to $300,000 per year,
Hmm.
and then that could be over multiple years. So
Hmm.
okay, so that we're good. We're good with that, but there's got to be the
Hmm.
return. So
Yeah.
let's get into why are they spending 150 to $300,000 a year?
Yes, yes, exactly. And so, in our experience with when we talk to plant managers in manufacturing, environments or factories, things like that, these plant managers tend to know the cost of their steam like down to the
They
millipenny.
do. And what do they measure? What's the unit of measurement for that they know it in? Is
Oh,
it dollars? Is it cubic
yeah,
feet? Is it
yeah, yeah. Well, dollars per uh,
time or
yeah, no. Per like volume of steam, dollars per
yeah,
volume
yeah.
of
So
steam. Put it
cubic
that way.
yards maybe or
Yeah.
something like that.
So
Yeah.
how right?
Okay.
How much steam you have to produce or you're consuming, and then how much it costs to produce that volume of steam.
Right.
So
Right.
so it's a rate. It's essentially a
Yeah.
rate.
Yeah.
And
Cost per volume. Okay.
yeah,
Yep.
and you're consuming steam as the
You're
factory's
consuming a certain
operating.
amount of volume of steam to do
Yes.
whatever you need to do, and they know if they have less volume or more volume, then there's going to be a cost associated with that
Yes.
volume, and then they're
Yes.
measuring
That's
it
right.
maybe probably cubic yards per minute, or I don't know, per hour or per second or something like that.
And so they tend to know that cost of steam very accurately.
Interesting.
And
Not surprising, but good.
yeah, yep. And then as far as maintenance goes, we time and time again we hear that they're just maintenance crews they're skeleton crews. They've they've reduced over time in the number of people who are there full time who are able to do maintenance on all the assets across the facility, not just steam assets. And so you're lucky if you have somebody who is just dedicated towards maintaining the steam system.
Yeah,
Usually there'll be a maintenance crew that's covering everything,
doing a bunch of stuff. Yeah.
doing a bunch of stuff. Yeah. And so to say, okay, how often are you inspecting your steam traps? Because they all know their steam traps fail. That's actually the numbers we typically hear from customers are on the order of 10 to 20% of the steam traps are failed. So they fail every roughly 5 years. Steam trap will fail every roughly 5 years, and um, we don't really get. I mean, those come from our customers. We don't get much
Hmm.
pushback when we talk about those failure rates. So those are
Okay.
pretty typical, and it kind of makes sense to me because if I were building a steam system, if that steam trap were having a problem and it was going to fail, the worst thing it could do is fail closed because then you get condensate backing up into your steam system, and that can do huge damage, cause explosions, even injury, casualties.
Right. Right.
So if you're going to err on one side, or the other, you err on the side of blow through, because lost dollars is a lot better than lost life. So
Yes.
okay, so that's kind of on the
So
failure
that's how
rate.
they're saving their money. You're saying, yeah, David. You're saying these guys know how much steam costs, and then if a steam trap fails, they're going to lose some of their steam, and they know the cost of
They
the
know the
steam they
cost.
lose.
Yep, that's
Okay.
exactly right.
So
Yeah,
let's put this into some actual numbers then. I mean,
mhm,
with the case study, so now we got the general understanding of what they're doing. They're trying to save lost steam,
correct,
and ultimately, I guess they're trying to save the energy required to make the steam.
correct.
Yeah.
Yep,
Okay.
yep, exactly
And then
right.
what type of then what are we looking at from an ROI perspective? Because they're spending good money here. I mean,
Yeah, yeah,
it's not
exactly.
nothing.
Yes. So, just to give you a sense, when a steam trap fails blow through, it will depend on a few factors. It'll depend on the cost of your steam, and that will vary at different facilities.
Cost of
Uh,
the energy to heat to create your steam,
yeah, the cost of the natural gas, for example, to create your steam, or if
right?
you're buying your steam direct from a utility,
Interesting.
it's the cost to buy it direct. So the cost of steam is one input to that model. The failure rate of the traps is another input to that model. The pressure of the steam is another input to that model, and think 30 psi, 60 psi is maybe typical. It goes up to a couple hundred psi.
Oh, okay.
And then the steam trap itself is the last input to that model. There are different types of steam traps. Steam traps vary in terms of their it's called an orifice size, but it's in terms of the size of the hole that the steam is allowed to pass through directly to the condensate when the trap opens.
Right, for the drainage, not the pipe itself.
Correct. Not for the
Yeah.
pipe itself. Pipe can be very big, very wide, big diameter in comparison to the orifice size. So when you pull all those things together, on average, when a steam trap fails blow through, you can expect roughly $100 to $200, kind of in that range, of lost cost, again, in your cost of steam, per week. Per week.
And
So
this is for one trap, you're saying?
for one trap. Yep. So time is of the essence in terms of fixing it, right? Remember we charge $300 a year for uh, our steam trap monitor for one trap. So if we alert you that a trap has failed and you go replace that trap and save, the time that it would have been blowing through
Yeah.
before maybe your next annual inspection, whenever that is. Maybe you inspect all your traps in January, but it failed in July. So
Mm-hmm.
now you're saving roughly 6 months of what would have been waste steam at a rate of $100 to $200 a week. And so when you pull all those numbers together, our general ROI is on the order of 6 to 7 times the annual investment is what our customers report to us that they're saving with this product. And the payback period is usually measured in about 2 to 3 months, meaning when they deploy the system or when the system's continuously deployed, they'll start seeing failures, trap failures. They'll go replace those, and then immediately once you've replaced a trap, you can now kind of count that in the
Yeah.
surplus bucket, right?
Yeah.
And
Yeah.
and based on that surplus of saved money, which again is very well known, very easily calculatable, it's usually a 2 to 3 month payback period.
No, I like it. And, just back of the envelope calculations, if I do your week and extrapolate it to a year, we're talking between $5,000 and $6,000 per broken trap. You're charging $300 more or less. I don't know if there's one sensor, if that's for one or two, but let's say
That's
$300.
one. Yep, that's
That's
one
one.
trap.
But you said on a trap you had two, so that's like six.
Well, we have
Now you don't.
two temp sensors. Two temperature probes, one sensor. So it's
Got it.
$300 per
Okay.
trap.
Okay. So
$300 per trap.
$300, yeah, per year, and then versus
Yeah.
if one breaks down, that's gonna be
Yeah.
five. Let's just make it 6,000 to make it easy. And then you're saying how
And
many of these broke
it's
down?
roughly a 20% failure rate,
Yeah,
right?
and a
So
20%
multiply.
failure rate. So yeah, that passes the sniff test. So we're looking at an awesome ROI, 6 to 7x. So multiple 100%, and then the payback in a couple of months.
Yeah.
Yeah, I like it.
We-
And then we're not even talking about the maintenance fees, but then we don't have to talk about that because of your business model, as you were saying, your business model actually absorbs that.
Yeah,
And
there
so
are no maintenance fees.
so you're incurring that and then you're passing along the savings to the
Yep,
customer.
that's right. Yeah, and it's funny, we see various talking to many customers. It's a range of say awareness of steam traps and steam trap monitoring at the different customers. Some of them will have very detailed records and scheduled usually annual inspection plans where they do go around and inspect every trap once a year. And again, imagine 1,000 traps. right? So
Yep.
there's 1,000 traps spread out on the second and the third floor in this sea of pipes, which looks like the Microsoft pipe screensaver, and you're trying to find the traps and then climb up and inspect them with a manual tool. So 20% of them are failed right now. Which 20%, which 200 are failed? So they'll have these very scheduled or planned maintenance routines. And then on the other end of the spectrum, we'll find customers who know they have a Steam system, they know they use Steam, they know they have Steam traps, but they have no idea how many they have, and they don't inspect them on a regular basis. And I mean, if I asked you how many outlets are there in your house, you would probably, I don't know, we probably got 100 in there or 50, I don't know, it's around there, right? And that's typically a response we might get is,
Hmm.
not exactly sure how many traps we have, but I guess it's probably around 100. We don't have the time or the energy to go around and inspect all of them. We're too busy with all these other things. And so where we can come in is help triage, help find those failed traps, get these customers on a continuous monitoring plan for their Steam traps, and then provide them the timely alerts to then go, do the replacement themselves or subcontract that out.
I like it. And I think there's a future in this. And the reason I say that is because I'm a big Star Trek fan.
Yeah.
And if I remember, when we get in with Geordi, and that's Next Generation, kind of my favorite, one of my two favorites.
Yeah.
There's steam everywhere in the Enterprise. I mean, like when there's a problem or they get hit by some photon bomb, there's
Yeah.
steam coming out of pipes. So this is like way in the future. So I
Yeah,
know
that's
for
right.
sure you guys have,
Yeah.
there's lots of monitoring, and maybe we'll be on
Yeah.
spaceships soon where they've got
That-
all these, these steam devices.
yeah, that's hilarious. Yeah, Steam has stood the test of time.
Who would have
So
thought?
absolutely. Yep.
David, how can people make contact and learn more about what we've been speaking about today?
Sure. Yeah. Well, we're obviously check out our website, everactive.com. We're also on social media. You can hit us up on LinkedIn or Twitter, or reach out to us directly at contact@everactive.com.
Perfect. Well, thanks. Very enlightening, and we'll talk to you soon.
I really appreciate it, Bruce. Thanks a lot.
Well, I hope you enjoyed the show. For notes and links, go to digitaloperatingpartners.com. Contact me if you'd like to discuss our consulting firm services or joining us by either becoming part of our technical ecosystem or one of our digital operating consultants. That is, if you're ICIP certified. And contact me if you know of a traditional private company for sale, one with EBITDA greater than $30 million and a business or products that seem like a perfect fit for digital transformation. And also contact me if your firm may be interested in raising a standalone digital transformation fund. We'd crush it. I'm your host, Bruce Sinclair. Thank you for listening. Until next time, may your path to digital transformation be a successful one.